So this video, we're going to focus on what we call a reaction diagram or potential energy diagram of a chemical reaction. And so this is just another way chemists can look at a chemical reaction and see what are the components to making the products. So I'm going to use an example of if I take the reaction between hydrogen and oxygen. I have two products I could possibly make. So one I could make is, of course, water, and another could be just combining them together to make hydrogen peroxide, so H2O2. So which way does this reaction go? Depends upon what we call its energy, and it's what we call its reaction progress. So I'm going to draw two graphs here, one right next to each other, and draw them relatively large on your notes, just because I'm going to put a lot of detail on there. So I'm going to put an XY graph right next to each other. So I'm going to do the first one on the left this way. So this is what we call a reaction progress graph. So reaction progress, you could really call this time. All it's showing is reactants going to products. So R is going to be reactant, P is going to be product. Okay. And then on your y-axis is going to be what we call H, enthalpy, or you could just call it energy for all intents and purposes. So what we have is we have a starting point for our reactant. So let's say it's hydrogen plus oxygen. Well, if we are going to make product, we need to understand is it an exothermic or endothermic reaction? So let's say, going back a long ways to first semester, we make a product of water, okay? And reactants are higher than products, so this is what we call an exothermic reaction. So you could write exothermic on the top there. Because the reactants are at a higher energy state than the products. Now, this is what we had you draw back in the thermo unit. We just left it at that. But this is coming back now because now we are talking about the chemical reaction. So in order for the hydrogen and the oxygen to react, they need to collide and they need to break their bonds and then form new ones. Okay, so what we're going to draw is what we call a reaction curve. So I'm going to draw that in here. Okay, so that's what we call the reaction curve. Now there's a couple points on here that I'm going to label that are going to be kind of important. So before I get to that, let's take the distance between the reactant and the product. So do that over here. This is going to be your delta H, so that is a negative value. So that's, we have considered that an exothermic reaction. I now want you to put a star on the top of this curve. Okay, the star, okay, the top of that hill is what we call the activated complex. And I'm going to give you a definition here in a second. So just write down activated complex or put a star there and come back to it when I show you the rest of the video here. And then I have from where the reactants are starting energy-wise to the top of that hill. So it's kind of, I always describe this as a roller coaster. So what this is the distance from here to the top of the hill is how tall is that roller coaster. This is going to be called E sub A. So E with a subscript of A, okay? This is what we call your activation energy. And every reaction requires some activation energy. So an easy example of this is burning a log in your fireplace. I need to light a match to start the spark to get it to go to the burning process of the combustion. So there are two new terms that you're going to have to know: activated complex and activation energy. Okay. Now, your activated complex, what I want you to think about is the hydrogen-hydrogen bond has to be broken and the oxygen-oxygen bond has to be broken. Well, once these bonds have, these molecules have collided and the bonds have broken, we now have what we call an activated complex up here, and I'm going to call it HO-HO. Okay, so I have all of the H's and all of the O's kind of gathered together at the top here. So I call this kind of the party. So everybody goes to the party. And then what is decided at the top of this hill is, okay, what product are you going to make? Are you going to make water, or are you going to make hydrogen peroxide? Or there could be a third or fourth option. So how this is determined is it going to release the most amount of energy? So if I make water here, I'm going to release the most amount of energy possible. That is a favored product. So that's generally what reactions try to do, is release the most energy. It doesn't like to require energy for you to make product. So this part here is what you call your activated complex. Now, the distance from the reactant to the top of the hill is the amount of energy required to get that reaction to go. So some definitions you could write into your notes, okay? And I will come back to the graph here in a second. Activation energy is the minimum energy particles must have in order to react. So again, it's kind of going back to the idea of collision theory. In order for a reaction to take place, they need to be moving enough in order for those collisions to take place. So that's what we call activation energy. So if you don't have that threshold, you will not make product. The activated complex is also called the transition state. So you're going to see both terms used in different contexts, but they mean the same thing. It is the arrangement of atoms at the peak of the activation energy. So again, it's my ho-ho example up here. It's just a big glob of all of the atoms, and they try to figure out, okay, what bonds are going to be formed. Is extremely unstable and extremely temporary. So I always, again, describe this as the party, because again, parties don't last forever. And so that's a gathering of people, and then eventually everybody kind of goes home after the party has happened. So activated complex and activation energy, you need to know those terms. So going back to here, so this is how we show a reaction curve for an exothermic reaction. So reactants will always be higher than the products. And this distance here from the reactant to the product is your delta H. And then the distance from the reactant to the top of the hill is your activation energy. And at top of the hill is called your activated complex. Well, what does this look like for an endothermic? Okay, so let's do an endothermic. Again, I'm just going to label the axes exactly the same. Okay, and again, reaction progress, you could call that time as well. So as we know with endothermic, okay, reactants are always going to be lower than the products. Okay, and again, if we're using this example of H2O2, now let's say the product is hydrogen peroxide. Let's say that's endothermic. So again, when we did this in thermal, we kind of left it at this, and you just needed to realize that the distance from the reactant to the product was a positive delta H. But now, understanding that these bonds are broken and then reformed into new processes, this is my reaction curve. Now, this is going to be slightly different. Again, activated complex is still the same. Okay, so activated complex is going to be, again, the ho-ho example. I use it just because it's funny. All right, then I have the distance from where the reactants are starting to the top of the hill. So this is a really tall roller coaster, okay? And if I don't go up that hill, I will not go through the rest of the ride. So this is my activation energy. So as you could see, endothermics, you got to go up a much larger hill than you do with exothermics. That's why usually exothermics are favored in chemistry, while endothermics are not as favored. Also note that the distance from the reactant to the product is still your delta H. Now this delta H is positive because again it is an endothermic process. So that's what we covered in thermo, so that's no different, okay? What is different here is the activation energy is much larger, and it is larger than the delta H, okay? And your activated complex is at the same place as it is with an exothermic reaction.